let's see a specific reaction in which we form a bond. So we'll talk about the reaction of hydrogen, one hydrogen atom with another hydrogen atom, and they come together, and we're going to form a molecule of H2. So again, here's our before the reaction, our starting materials, and then we make molecular hydrogen as our after. So what does this look like? We're going to look at this from an energetic standpoint. So we need our axis. Here's our energy axis. So here's high energy, and here is low energy. And here is one of our hydrogen atoms. And it has an orbital. It has an atomic orbital, and that atomic orbital specifically is a 1s orbital. And that 1s orbital has a single electron in it. So that is one hydrogen atom. We're going to draw the other hydrogen atom over here. We're going to put it at the same energy because it's also a hydrogen atom. This is also a 1s orbital. And it has an electron. Doesn't matter whether we point that electron up or down. It's all the same. And so here's our before for one hydrogen atom. On the right is our before for the other hydrogen atom. And now we're going to bring them together in the middle, and that's going to be our after, and we'll see what happens. So these two atomic orbitals are going to mix together. Remember, these are AOs, atomic orbitals, and they're going to mix together. I'm going to try to draw these equally up and equally down. They're not perfect. But so what happens is we now form a new molecular orbital, two new molecular orbitals, because we put in two atomic orbitals, and these electrons are going to now fill up the new molecular orbitals, and they fill it from the lower energy to the higher energy. We have two electrons. We can fit both electrons in a single orbital, and this is the Aufbau principle where we fill from the bottom up. And so here's our new bonding picture. This is our bonding orbital. Specifically, it's a single bond or a sigma bond. That's supposed to be the Greek letter sigma. This orbital is called antibonding. Kind of weird, but we call it antibonding. It's also a sigma bond, but it's sigma star, and that star indicates that it's not a bonding situation, it's an antibonding situation. Now, this orbital is also vacant, the antibonding orbital, while the bonding orbital is a filled orbital. And you might say, who cares about the vacant orbitals? There's nothing there. It has no consequence. Well, as it turns out, it does. And lots of reactions occur when things with excess electrons are looking for somewhere to dump those electrons. And so what do they look for? They look for a vacant orbital that has capacity to accept electrons. So vacant orbitals are very important for reactivity, although I admit they're not quite as interesting because they don't, at least in the current picture, hold any electrons. So this energetic picture of how we form H2 gas actually demonstrates why H2 gas is more stable than two hydrogen atoms by themselves. It's because the electrons, when you form the molecule and you form the new molecular orbitals, these electrons go down in energy. There's a change in energy that occurs. With each electron, they both go to a more stable position, and therefore there's a release of energy, and this structure is actually the molecular structure is more stable than the two hydrogen atoms in isolation. So that is a nice simple bonding picture for the hydrogen molecule, looking at it from an energetic perspective.